So, good evening, students. Welcome to the last session for this analog circuits course. I'm Disha Devi, a PMRF fellow from IIT Gandhinagar. So, in today's session, since yesterday you people had a lot of doubts, so let's make this session a doubt session. And we can first clear the doubts, then I can take up a few problems based on the concepts discussed yesterday. So, am I audible clearly, all of you? Am I audible clearly, students?
Yes, ma'am.
Okay, is my screen visible?
Yes,
Okay, so maybe we can solve doubts today. So, if anyone has any doubts, you can bring up your doubts and we can clear the doubts. Any doubts regarding exams, any problem, any concept? I guess somebody raised their hands, no? Okay. Yes, any doubts?
no, ma'am.
No doubts?
Yes, ma'am.
Okay, anything you want to ask you people, or else should I move to some problems that I have already prepared?
Yes,
So,
ma'am. You can move.
okay, so we can move to the problems then and we can come back for the doubts.
Okay.
So, uh, yesterday we discussed relaxation oscillators, right? Waveform generators and relaxation oscillators. So, our first problem is related to that. So, here in this particular circuit, what type of circuit is this? Can you relate to the circuit? What type of circuit is this? Have you seen this circuit anywhere? Yes. What type of feedback is given in this circuit? What is the feedback? What type of feedback is this? Yes, anyone? What type of feedback is this?
Positive feedback.
Yes, this is a positive feedback, right? So where have we observed a positive feedback? And this VR is nothing but V reference, right? Reference voltage. So there is a reference voltage given to one terminal and there is a positive feedback. Where did we see this kind of connection? Yes, where was this kind of connection observed? Yesterday we saw this in the Smith trigger, right? Smith trigger circuit. We saw this kind of connection, right? Where output was fed to input via positive feedback. But there, the reference voltage was being observed through this resistor connected circuit, whereas this is the reference voltage. So the question is, for the circuit given below, find the VR, this, that is this value VR, and R2. So we have to find out R2 and VR when R1 is 8 kilo ohms. It is given that VTL is 0, VTH is V by 5, and L plus L minus is V. So what is this L plus and L minus? These are like the limits, and these are given as V. So we know that the higher limit and lower limit for our output is already fixed. It is either L plus or L minus. Now the question is, if this Vi, that is the input, if this Vi becomes equal to VTL, that is, if the Vi, that is this voltage given here, it becomes to lower threshold voltage, then our output should come out to be plus L, right? So, and we know that VTL, and so here if it is VR, at this node it is VR, we will find this VTL and VTH from the feedback path, and from there we know that VTL would be, VTL is when the threshold is at lower voltage, then with VTL, if Vi is VTL, then Vout will be plus L, right? So if this is plus L, this is VR, then the voltage VTL is nothing but VR times of 1 plus R1 by R2 minus L plus R1 by R2. Okay, this comes from the KCL equation, and if Vi becomes equal to VTH, V naught will come out to be minus L. Similarly, the way the Smith trigger works, as we have seen yesterday, that as you touch the upper limit, your output flips, right? So that is the reason. So from there, we'll get VTH as VR 1 plus R1 by R2 minus L minus times of R1 upon R2. Now here it is already given that VTL is 0. So it is 0 equal to VR 1 plus R1 upon R2 minus L plus was nothing but V. So substituting V into R1 by R2, and was V by 5. So substituting V by 5 equal to VR 1 plus R1 by R2 minus V, L minus is minus of V. So this becomes plus V R1 by R2. Now here unknowns are R2 and VR, right? So We need to solve these two equations to find the value of R2 as well as VR. So let's do that. So we can take V common, so all the V will be cancelled. It will be 1 by 5 R1 by R1 plus R2 into R1 plus R2 by R2 plus R1 by R2. These two are cancelled. So we get 1 by 5 is 2R1 by R2. So R2 is 10 times of R1. So R1 was, how much was R1? 8 kilo ohms. So if R1 is 8 kilo ohms, then R2 becomes 80 kilo ohms. So we have already found the value of R2. So R2 is found. Then we need to find the value of VR. VR is V times R1 by R1 plus R2. So VR becomes V times R1 is 8 by 80 plus 8, that is 88. So V into 8 upon 88, we get VR as V by 11. So this is the voltage. Hence the option is V by 11 and 80 kilo ohms. Okay. So is this clear? So here we didn't do anything. Here it was just applying KCL. We found these equations. And similarly here also KCL, by using the KCL we found the equations. We simply substituted the value of VTL and VTH and the corresponding output values, and we simply found out the results. Any doubts? Any doubts in this particular problem? It was simply a straightforward calculation, right? Is this clear?
Yes, ma'am.
Okay. So moving on to the next problem. So in this problem, here it is asked that what kind of output will this circuit below give? So before going into the whole circuit, what is this particular circuit? What is this circuit? Have we seen this kind of circuit before? Yes, have you seen this circuit before? What is this circuit? When you have a capacitor and feedback and there is a resistor, this can
Integrated.
yes. So this is an integrator, or it can also be a low pass filter. Because integrator and low pass filter are they both have the similar profile. It's just the frequency range where you are operating. It defines whether the system will or the circuit will behave as a integrator or a low pass filter, right? Because if we see the profile for that particular circuit, it is somewhat like this. So when you use the frequencies in this range, so here in the passband range, if the frequencies are in this range, it behaves as a low pass filter. When the frequencies are in this range, this particular circuit acts as an integrator, right? So considering that we are using it as an integrator, since we want to find the waveform, right? So for waveforms, we need to have some relation with that of waveforms. So that's why. So this particular part is an integrator. Now, what about this part where one terminal is grounded and other terminal is connected through two resistors? So what is this circuit? Have you seen this circuit before? What type of circuit is this? Yes, what is the circuit this? What type of circuit is this? We discussed this circuit before, right? Okay, what type of feedback is this? Is it a positive feedback or negative feedback? First of all, observe the feedbacks. What type of feedback is this? Positive or negative?
Positive.
Negative.
Yes,
Positive.
it is a positive feedback, right? Now, two resistors have been connected uh, back to back, but in positive feedback. Then, what kind of circuit is this? Yes, what is this circuit? This is a Smith trigger, right? Isn't it a Smith trigger? Where you have positive feedback and you have two resistors, and based on the feedback, these feedback resistors, you will have the values, right? So this is a Smith trigger. Now we know that a Smith trigger gives us what type of wave? What is the output of a Smith trigger? Yes, what is the output of a Smith trigger?
Triangle.
Triangle. Why is the output of a Smith trigger a triangle? Smith trigger gives you a square waveform, right? When you have a Smith trigger, you get output as a square wave. That's what we discussed yesterday, right? It was converting a sine wave into a square wave, or it could convert similar to sine wave also into a square wave. So since this is a Smith trigger, it will convert the whatever signal. It is definitely going to be a periodic signal. And where will you get that periodic signal from? So there is this capacitor, right? This capacitor will charge and discharge. Based on that, you will get a certain signal at this point. And since this is at 0, so comparator will be activated. And from there, you will get your output as a square wave. Now, if second part gives you a square wave, and that this output here you are getting a square wave. Now this square wave is being fed into your integrator, right? So if a square wave is being fed into the integrator, then what will be the output of the integrator? Yes, what is the output of integrator? If you integrate a square wave, what will you get as output?
Triangle wave.
Triangular wave, yes. So at this point, you will get your output as a triangular wave. Now see, this will be self-sustained because the moment this node observes a triangular wave, the triangular wave will uh, act as the next stage for the or the input for your Smith trigger, and from there that triangular wave you will again see a square wave formed, and then that square wave is fed into your integrator and you will again get a triangular wave. So this circuit will give you two waveforms. One is a square wave and another is a triangular wave. So the first output that you observe after the capacitor is a triangular wave, then followed by a square wave. So these are the outputs. Sine wave, where are you getting sine wave from? There is no sine wave here, right? Okay, to get a square wave. So see, the idea is you will get two thresholds from your Smith trigger, and you need to have some kind of waveform so that which can cross both the thresholds to give you two outputs, like two saturating output plus VDD and minus VDD, which is required or which is the output of a Smith trigger, right? But it is like not necessary that you only need to have a sine wave. See, if I have a triangular wave, then also the conditions still remain same and your Smith trigger will work as it is, right? Be it a sine wave, square, triangular wave, or it will also work for let's say a sawtooth wave, because we are not concerned about the waveform or the slope of the waveform or the what should I say, the expression of the waveform. In Smith trigger, we are uh, only concerned about the levels, threshold levels. So yeah, so it can be somewhat like this, right? So this type of distorted triangular wave also will give you similar outputs. Now there was another question. The question was that, okay, how can it give us a square wave without any input, right? So see, again here it is, so there is a capacitor element, right? Whenever there is a capacitor, definitely charging and discharging of capacitor happens. So let's say in one cycle, like in the beginning you just connected the capacitor didn't have any charge, and now based on output you will have some output at the output, right? It can either be plus VDD or minus VDD. Based on that, your capacitor will either charge or it will discharge that particular output node through this path. So this is the path, right? So this path will be taken for capacitor charging as well as discharging. So through this, when capacitor is charging and discharging, you will see a certain waveform at this particular end, which is actually acting as the input to your um, Smith trigger, because that is the node, or yeah, because that is the node, or this is the node where you are comparing your comparators comes into picture, right? So here or here, anywhere you can say, you will find a certain waveform which is definitely oscillating across your zero. So from there it will pick up that particular signal and then it will transform it into a square wave. And the moment it transforms it into a square wave, you have your output as a square wave. And when you feed that output to a triangular or an integrator, it will give you a triangular wave. Is this clear? Okay, so to charge the capacitor, where is that input coming from? Again, see, it is a closed loop network, right? So it has to start from somewhere. So it will again start picking up on the small noises which are present. Because in this closed loop situation, you don't have any input. So you will depend on the noise, as we do in case of oscillators. So in the similar case, here also you will depend on the noise. Yes. Yeah, you people can unmute yourself and ask. That would be easier because there might be a possibility that messages might be missed. So, anyways, so you people understood these waveform generating circuits, like how the waveforms are being generated and how we are getting a triangular and square wave out of these. Yes, is this clear? Any doubts? Okay, if there are no doubts, maybe we can move ahead. So, in this question, it is about multivibrators. So, which multivibrator has the ability to return to a stable state from an unstable state, and which multivibrator keeps on transitioning between one state to another? So, have you do you people know or have you people studied about multivibrators? Yes, have you people gone through multivibrators? What do you understand by multivibrators? Yes, anyone? What are multivibrators? What are multivibrators? So see, multivibrators are also the circuits similar to that of oscillators. Through multivibrators also, what you can get are either square waves or pulses, and it depends on what type of multivibrator it is. Mostly there are two types of multivibrators. One is astable multivibrator and another is a monostable multivibrator. So when we say it's an astable multivibrator, what we mean is there is no stable state in the output of the multivibrator. So multivibrator is switching between two states and they both are not stable. So basically what happens is the output stays high for some time, then it goes low for period of time, again it goes high, then it comes down to low, and it goes high and goes low, and continuously it is switching, right? So since it is switching continuously, so there is no single stable state. That's why this kind of output, when a circuit provides us, we call it as an astable multivibrator. Whereas in case of monostable multivibrator, as the name suggests, in monostable multivibrator, there is a single stable state. So what happens is, in monostable multivibrator, what you do is you introduce a trigger, or basically you interrupt the circuit a little, So because of which, what happens is you find a pulse is generated. A pulse is generated, and again it comes back to the stable state. So a pulse is generated, which is basically a disturbance, and this pulse's duration depends on the disturbance's duration. What is the duration for which you are introducing a disturbance? That defines the width of the pulse or the size of the pulse, and after that, your state or the output comes to a uniform state. So this is actually the stable state, and this is the instability that has been caused. So since there is a single stable state in monostable multivibrator circuit, so that's why it is called monostable, right? So here the question is asked that which multivibrator has the ability to uh, return to a stable state from an unstable one. So which of the two multivibrators does have a stable state? Like, first of all, astable multivibrator does not have any stable state. Only monostable multivibrator has a single stable state, right? And so that's why this is monostable multivibrator. The explanation is for a monostable multivibrator. And whereas here it is given that which multivibrator keeps on transitioning from one state to another on its own. So here, as you can see, for an astable multivibrator, it is oscillating between two states. It goes high and then comes low. Again, it goes to high and comes down to low. So this is the situation which is referring to an astable multivibrator. So one is monostable multivibrator, other is astable multivibrator. And in case of bistable multivibrators, so there are again two states, and this kind of square wave that is being generated, it can also be referred to as bistable multivibrator because there are two states. But most of the time, this particular behavior we refer to as astable behavior only. Okay, and yeah, then what else? Okay, so the basic relaxation oscillator that we saw yesterday using Smith trigger, the basic relaxation oscillator we saw yesterday using a Smith trigger was from here, maybe there will be an R followed by a C. Yeah, this is what the circuit was, right, yesterday. So we saw that the output of this particular circuit was again a square wave. So this is one of the astable multivibrators. So we can call this particular circuit also as an astable multivibrator, as it gives us a square wave which does not have a stable state. Stable state, the idea means that that particular state, when you see it in a steady state situation, so uh, the system is in that particular state. So that is the steady state and a stable state. So this circuit is also known as a stable multivibrator. Other than that, astable multivibrators or monostable multivibrators can be designed using 555 timer ICs. So 555 timer ICs, 555 timer IC is used for designing astable and monostable multivibrators. So, have you people come across this 555 timer based circuits for astable multivibrators and or monostable multivibrators? Anyone? Have you people ever come across these particular circuits using 555 timers?
No, no.
Or do you people want me to go through these circuits? Yes. Do you people know these circuits, or do you want me to go through these circuits once? I could not understand what is yes, ma'am. Do you want me to go through, or do you know these circuits? Okay, you people don't know. So this 555 timer IC. So these are so this particular IC is used to generate or to design timers. We all know about timers, right? Say a 5 minute timer, a 10 minute timer that you have in your mobile phones or anywhere. Um, how does that timer works? Like, so for designing those timers, this particular timer IC is used, and you can use the same timer IC to design multi-vibrator circuits as well. So if I show you how those circuits look like, maybe I can quickly draw. Okay, if I talk about the IC, it is a 6-pin IC, right? Yes, it is a 6-pin IC. So it is 8, 4, 7, 2, 6, 3, 5, 1. I have randomly numbered them for the sake of how it looks in the circuit, but the pins will be sequentially numbered. So 1 2 3 4 5, 1 2 3 4 5 6 7 8. So you will have two series of pins. One side you will have four pins, other side you will have four pins, and the sequence starts in a similar fashion. So it starts from 1 and then you continue with 8. So here I have written it like this to just show that how you connect different pins in the IC to make it work as an astable multivibrator. Okay, so let me quickly finish the drawing first so I can explain to you. Right. So this particular circuit that you are observing right now, this is the internal circuit of the 3 5 timer, and the numbers that you are seeing in brackets are actually pin numbers. So in brackets you have pin numbers. So this particular IC consists of two op amps and one RS flip flop and one switching element inside. So here this is the switch. So here for switching I have shown a transistor. So there must be a transistor or a MOSFET inside for the switching operation. So this is the internal circuit of the IC. So maybe I can enclose it. Okay, so this is IC 555 timer IC. This is what is inside the timer IC. It has two op amps followed by an RS flip flop and a switch. Okay, so RS flip flop will give you the output, and since it is a flip flop, it can store a high or a low value. In a practical scenario, it will be plus 5 volts or a 0 volt. So when output is 5, Q bar would be 0. So based on that, you would see it is either connected. So if the transistor turns on, then the current will flow through this resistor inside the transistor and it will be grounded. If the transistor turns off, your current flow direction would be from VDD to R1 to R2, then C. So the capacitor charges. And if the transistor is turned on, the capacitor will also discharge through the transistor, right? Because this is the low resistance path, right? As it is directly connected to the transistor. So that's how the two states of this RS flip flop will define whether it will make the like the capacitor charge or discharge. And as we know, as the capacitor charges, the voltage at this particular node will start to increase, and you can see that there is one node which is connected to VULT and other is connected to VLT, right? So these two comparators will come into picture, and these two, based on these two comparators, your R and S value will change. And if you are aware with the flip flop, so RS flip flop has like what are the situations, like when it sets, when it resets, when it is in hold state. So you can look into this in digital. So based on those combinations, whether it is 00, 01, 10, 11, depending on that, your output of the flip flop changes, and based on that the switching operation happens. And with that, it defines whether the capacitor is charging or discharging. So if you look at this, the circuit that you are looking at right now, this particular circuit is for a stable multivibrator. This is the circuit for a stable multivibrator using 555 timer. In the similar fashion, you can have a monostable multivibrator using the same 555 IC. Maybe I can quickly draw and show, and we can also discuss like what is the difference between the two. Okay. All right. In case of monostable multivibrator, as I mentioned, we will have one trigger which is there. In a stable multivibrator, you don't need any inputs, and it will be continuously switching from a high to low, then high to low. It is continuously going on and off, on and off, on and off, right? But in monostable condition, it is always in a stable state. But when you interrupt the circuit a little bit, how you interrupt it? Through a trigger signal. So when you introduce a trigger signal, your output suddenly goes high for a certain period of time, and it generates a pulse. The width of that pulse is dependent on what is the trigger, like based on the time period of the trigger. And so that's how it goes into an unstable state once, giving a pulse. Again, it comes down to, yeah, the stable state. So definitely you would need a position or a pin where you can introduce a trigger signal, right? So how you introduce a signal is, see, the circuit remains same, but here, rather than using two resistors, we will use one resistor followed by a capacitor. One resistor followed by a capacitor. This particular position only connects to this. So this is pin number 5. This is pin number 6. And at this node is what you provide a pulse signal, which is actually a trigger, a small disturbance. and it is actually the lower value. So this is at VDD and here it is at VDD by 3. This amount of pulse is what you apply for the working of monostable multivibrator at pin number 2, and then other than that, this is pin number 7, this is pin number 4, pin number 3, all of them remain same. The only thing that is different between a monostable multivibrator and a astable multivibrator is this particular trigger signal that you are providing. So based on this trigger signal, what happens is when you provide a trigger signal, uh, no, so this is VDT till 0, and here VLT is VDD by 3 and VUT is 2 VDD by 3. This VUT, the signal is actually 2 times VDD by 3. So upper threshold is 2 VDD by 3, lower threshold is VDD by 3. So what happens is when we apply a pulse of VDD, and this is 0, a lower going pulse, the capacitor, this particular capacitor starts to charge, and it charges with the expression of 1 minus e to the power minus t upon RC, and it reaches the value of 2 VDD by 3, which is the value corresponding to the upper threshold. So since upper threshold is triggered, so the output will become 0. So here you will have a reset, and because of reset your Q flips. So until now, if the capacitor was charging, now it will start to discharge. So it discharges, and if this is your trigger, this is Vc of t, then corresponding to this particular charging of the capacitor, you will observe an pulse. So this is your output. So you will see a single pulse where this particular T on is nothing but the pulse width. Right? This is the pulse width. And this basically monostable multivibrator circuit is used to generate pulses when you want certain pulses with some length, then you will use these monostable multivibrator. If you want square waves, continuous square waves like clocks in our digital signals, then those clocks can be generated using a relaxation oscillator or through the timer IC by using this astable multivibrator circuit. Okay, is this clear? So this is how we use a 555 timer IC for designing astable multivibrator as well as monostable multivibrator. All right. So yeah, let's move on to the next problem. So in this problem, uh, which of the circuits is a voltage to frequency converter multivibrator? So here what you want to do is you want to convert voltage to frequency. So how can you do that? Here the astable multivibrator, the charging and discharging of our capacitor depends on what is the supply, what is the VDD that you are providing, right? And if you change the VDD, based on that, the charging time as well as the discharging time will be changed. So if you have very high VDD, the charging would be faster. So the pulses will be smaller. Hence, your frequency would increase since the time period is less. Now, if your VDD is small, like the potential that you are applying here is small, so what would happen is it will slowly charge to reach the certain threshold that is needed. And because of that slow charging, what will happen is your it will take longer to charge to the desired threshold level. So your time periods increase, and since your time periods increase, your frequency will be reduced. So that's why the output frequency of astable multivibrators can be controlled through the input voltages which are applied to them. Hence, the astable multivibrators can be used as voltage to frequency converters. Okay, so by using astable multivibrators, we can convert voltages into frequencies. Like, yes, the amount of voltage, higher the voltage, lower will be the higher the voltage, higher will be the frequency, lower the voltage, lower the frequency. So that kind of relation you can obtain through astable multivibrator circuits. Okay. Now coming to next problem. So in this problem, it is asked that consider the following two statements. Statement 1 is astable multivibrator can be used for generating square waves, and statement 2 is bistable multivibrator can be used for storing binary information. So which of these is true? So only statement 1 is correct, statement 2 is correct, both 1 and 2 are correct, both 1 and 2 are incorrect. So, uh, if I say that this particular circuit that we are calling a stable multivibrator, we can also call it as binary multivibrator. Why binary is because there is a flip flop here, right? The RS flip flop. This is our RS flip flop, SR flip flop. And we know that any flip flop can store one digit. So it can store one digit, which is a binary number. Either a 0 or a 1 can be stored in a flip flop. Now, since it can store one digit, which is binary in nature, that's why this particular multivibrator circuit can also be called as binary multivibrator. Now, coming to the question itself. So, in this question, we definitely know that astable multivibrator can be used for generating square waves. We have already seen that through both the circuits, the relaxation oscillator type of multivibrator circuit as well as through the 555 timer circuit, that in both the cases we get square outputs. So square wave, this particular statement is correct. Now when we say that bistable multivibrator can be used for storing binary information, this is also true, and that is because since it has a single flip flop inside, and that flip flop can store one digit, which is either 0 or a 1, that is a binary value. That's why it is also known as bistable multivibrator. So both statement 1 and 2 are correct. Okay, so astable multivibrator generates a square wave, as well as bistable multivibrator can be used for storing binary information because of the presence of flip flop inside the bistable multivibrator circuit. Okay, so yeah, both the statements are correct. So that's it for today's problem. These were the problems based on multivibrators as well as the Smith trigger circuit that we discussed yesterday. Now I can take up problems like your doubts session. So we can have doubt session now. So yes, any doubts regarding any concepts? So did you people understand the problems that were discussed today? Any doubts in that? Yes. Are there any doubts in the problems that we discussed today? Or if not, do you have any other doubts regarding the course, regarding exams?
I
Any
have
con?
doubts regarding assignment, madam. In last class, we had seen two problems now.
Yes. What were your doubts?
Shall I share?
Yeah, you can share. We can discuss, take up those problems. And meanwhile, there is another session at 8 p.m. So you can attend this that particular session for more problems. Right. Okay. Yes. What was the question?
Is visible, madam?
Yes, your screen is visible.
This question number 4, madam.
Okay. A feedback arrangement is shown in figure such that x naught is 5 volts, xf is 0.5 volts. Okay. And x is 1 volt. Find the amount of feedback. Find the amount of feedback. So if Vf is 0.5, x naught is 5, then it should be 0.1, or like what is, like, find the amount of feedback. What do they want to ask? Yes, xf is 0.5 volts, x naught is 5, a beta, this is x naught, this is being fed, here it is xf, this is going up, here is the summation, this is a negative feedback. Okay, this is coming as positive, and xi, right? Yeah. So what is the question? Can you show the question once again? Xs. Xs is 1 volt. Find the amount of feedback. Amount of feedback means, are they asking for beta?
No, madam. The above question is beta.
Okay.
So it is 0.1. I did not understand this fourth one. Find the amount of feedback means what? What is their intention? I don't
Find the amount of feedback. What are the
know.
options? What are the options?
1, 1.5 to 2.5, madam.
1, 1.5, 2, 2.5.
So amount means I thought it's a voltage, but in problem they are already given XF.
Yeah, it's already given, right? So 1, 1.5, 2, 2.5. Okay. This is not beta, right? Yeah, because
Actually, I did
options
not
will,
understand the question, madam. Before question is
yeah,
beta.
because beta it will be 0.1, but
Yes,
options में there
madam.
is
The
no.
above third question they are asked find beta. So which
Right.
is this one XF divided by X naught. So we'll get point
Correct.
1.
Correct.
And coming to fourth question, I don't know the context of that amount of feed.
X is minus xf. What is the answer?
They are given 2, madam.
Oh, answer is 2.
Hmm.
Amount of feedback. Any explanation, anything given for this? Like, do they have any solution given to this
In
problem?
solution, they wrote 1 plus a beta, madam. How long it is correct, I don't know. I open that also.
1 plus A beta.
They write 1 plus a beta is the amount of feedback. So in which
Oh, okay, okay, okay. So it's like, see, when we have a feedback, especially a negative feedback, our gain turns from A to, it becomes A upon 1 plus A beta, right? So this particular factor of 1 plus A beta, they are reporting it as amount of feedback.
then we cannot call it as a feedback amount, na, madam. 1 plus a beta. How can we call that
It's,
as a feedback amount? It's a factor which we are dividing the
yes, yes. So it is the factor that comes because of feedback, right? It's the consequence of feedback.
but it is also
1 plus
having
A
a
beta.
gain, na, madam.
Yeah, yeah. 1 plus A beta is like the factor that comes because of feedback. If there was no feedback, you will not get that factor, right? So, okay, but is it called the amount of feedback? Actually, this nomenclature is new to me as well. So, I don't know.
If
Amount
this
of.
type of questions will give how to answer, madam.
Uh,
So I am
like,
I am not
was
following
this.
this word amount of
What
feedback.
was this nomenclature used in lecture anywhere
No, madam. No, madam.
while discussing A plus 1 plus A beta factor?
No, madam. They are not used that nomenclature.
Oh, they have not used that nomenclature
Mm-hmm. Yes.
because this also slipped my mind. Like I never came across the amount of feedback. Okay, because it is the feedback. Uh, what can we say? 1 plus A beta is the factor that comes into picture.
Yes, madam. We can call
But
it as actually factor.
yes, but
If it is input resistance, we are multiplying with this factor. If it is output resistance, we are dividing with this factor.
yeah, yeah, no, but yeah, it is called feedback factor. Feedback
Hmm.
factor is the nomenclature used. So this is feedback factor.
So if it is the voltage, 2 volts is not feedback, no, madam. They are given except as 0.5 volts.
Sorry,
They are written this as 2. Is it 2 volts or only number? It's a number.
it should be a number. It is a number because 1 plus A beta is like because beta is also similar to gain, right? So it is unitless, and A is also unitless. So that's why 2 is a factor. So this is feedback factor actually. Yeah. Amount of feedback, this nomenclature is a little new to me also, but this is known as feedback factor for sure.
Hmm. And
Yes.
one more is in the same week for sixth question, madam.
Okay. What was the question?
This one.
Ah, okay. Consider the circuit arrangement and the figure. Let me quickly draw the circuit.
Hmm.
A, B, here it is VDD by 2. And this is being fed through. This is R. This is GM. Okay, this is GM VG. GMVG. Acha. This is VDD. Where is GMVG? Okay, VG is here. Oh, all right. Hmm. Okay. So consider the circuit arrangement and the figure given below. Find the signs of op amp A, B for negative feedback.
In the lecture, these type of questions they are not explained. In problem solving also these type of problems they are not explained. And from
Okay.
where we can answer these type of questions?
Signs of A and B for negative feedback. Oh, okay. Mm, this is VG, this is GMVG. GMVG means it's like MOSFET. Oh. Okay, so what was the answer? Accepted answer?
Madam?
What is the accepted answer?
Minus plus, ma'am. A is minus and B is plus.
A is minus and B is plus, right?
Hmm.
Okay. Maybe I can share my screen and then we can analyze this.
Okay. And in the following question, this one they are given, madam. They are asked VDD by VG value.
VDD by VG. Okay,
Seventh
maybe.
question is VDD by VG.
Okay. And question number 7 is VDD by VG. And what was the
They are
answer to
asking
that?
that ratio.
VDD by VG. What is the answer to that? Should
Madam,
be GM. What is the answer to VDD by VG?
they are given 2 GM R.
2 GM R.
Hmm.
Okay, okay. All right. Yeah, I'll share my screen.
Okay.
All right, my screen is visible, right? Is my
Yes.
screen? Yeah. Oh, okay. This is the circuit that we have. Now, see, by looking at this circuit, this is VGGM. If I tell you that this is a small signal model for a MOSFET, would you believe that? Would you believe if I say that this is a small signal model for a
It should be
MOSFET?
GM VGS, no, madam.
Yes, but
But they wrote
considering
the
that
VG.
source is grounded, and moreover, this is the diagram for a CS mode amplifier. What do
I
I
have
mean
one more
by?
doubt, madam. If source is connected to ground, the amount of
Yes.
current to source terminal is zero, right, madam?
Sorry.
You are saying that source is connected to ground, then the
Yes.
amount of current through source is zero, right?
Why?
It is connected to ground, no, madam. What is the potential at source point? It is zero.
No, no. See. I'll draw this diagram in a more familiar way. Okay. So this is the small signal model that you are seeing. I'll draw in the circuit model so it will be clear to us. See, there is this MOSFET A and B. The output of the output of op amp is connected to this MOSFET, and in one terminal you are giving VDD by 2. In other terminal, you are connecting this terminal to this point. This is drain, this is gate, and this is source. And for a MOSFET, how does the small signal model look like? This is this is gate, this is source which is grounded, this is drain. Here you have a current source which is GMVGS, this is plus minus VG, and here you have D, and the resistor that is connected to the VDD, that resistor would also come here and it will be grounded. So this is basically AC ground, right? So this is how, and this is where you take your V out. Okay. So now the question is, you want to observe a negative feedback. All right. So we know that when a transistor is connected, so this is CS amplifier. This particular configuration is nothing but a CS amplifier. In a CS amplifier,
Shall I ask one question, madam?
yes, wait,
Say
VG
it is a CS
to,
amplifier,
yes,
and for amplifier we have to provide only AC signals, right, madam? If it is amplifier designed with BJT or FET, they are capable of amplifying only AC signals.
yes.
Then how can we say this as an amplifier, madam? Because
Why?
the input is DC voltage. VDD by 2 means it's a DC voltage.
VDD by 2 is a reference voltage, right?
Yes, madam. It's a DC voltage. Am I correct?
No, VDD by 2 is a DC voltage, but it is also a reference voltage, right? Reference would be a DC, right?
Yes, madam. Then how this MOSFET acts as an amplifier in this context?
No, I'm talking about the circuit that it looks like. So if I draw the circuit equivalent, this is the circuit that you will get. And this is the circuit when you have a resistor connected with a MOSFET in this fashion. This is actually CS amplifier configuration. Now, whether this amplifier is working, is it biased, not biased, is it in active phase or not, that is a different story. But the configuration is what I'm talking about.
Configuration, okay, ma'am. If we don't know the biasing, how can we know whether your MOSFET will provide a negative feedback or a positive feedback? If it is operated in active region, then we can consider it as an amplifier. So it will provide 180 degrees phase shift.
Yes.
From that, we can conclude that whether we are providing negative feedback or positive feedback to op-amp. So here we don't know the region of operation of MOSFET, then how can we assign negative and positive to op-amp?
Madam,
But see, when you have this GM-VGS, no, when you write it in GM-VGS, when you get this GM and VGS, you get this GM-VGS in MOSFET's output. This is only possible when your MOSFET is working in saturation region. Then only you can write or draw the MOSFET model in this fashion. This is not the MOSFET model for a linear operation. Do you get my point?
Yes.
When your MOSFET is operating in a voltage controlled current source configuration, which is in saturation, that is only a situation when you can draw this GM-VGS in the output side of the MOSFET. This is MOSFET's equivalent in its saturation situation. This is not MOSFET's equivalent in its linear region of operation. Okay? So which basically shows that our MOSFET is on and it is working. So it is already in saturation. And now since the MOSFET is in saturation, this CS amplifier will also work. And since the CS amplifier is working, we know that the phase difference between VG and VD in a CS configuration is 180 degrees. So this phase in a CS amplifier is 180 degrees. So you are feeding 180 degrees phase to your, like out of phase signal to your input of op-amp. Are you satisfied with my argument?
Little bit confusion, madam.
Where is the confusion?
This MOSFET is providing 180 degrees phase shift.
Yes.
And this MOSFET is there in the feedback path.
Yes.
Then 180 degrees signal is coming. So from that we can conclude that A is negative.
Yes. A is negative.
And here one more thing, madam.
Yes.
If this is negative feedback,
Huh.
and what will be the amount of current flowing through this negative terminal?
Which negative terminal?
I mean A.
Will there be any current flow in A? We know that there is no input current flowing in A, right? Does any current flow inside the op-amp?
Ideally, we can speak 0, but feedback current will be there.
Practically also it will be 0 because it is directly connected to the terminal, right?
If it is ideal case, we can say 0, but practically it should be in some nanoamps, right?
No, there should not be. If it is a MOSFET based op amp, you would not have any input current. There won't be any gate current.
Okay.
Practically also in MOSFET, there should not be any gate leakage. If there is gate leakage, that means your MOSFET is defaulty.
Oh.
Yeah. Right? So is this clear?
Madam?
Yes.
Can I speak?
Yes.
Yes, madam. Generally, in this type of problems, in other analog circuits, not analog circuits, basic electrical circuits, course video, they have suggested to put a what we call as our test voltage at the output of the op amp.
Okay.
Output of the op amp and replace the op amp or something like that they have told. I don't know correctly now. But if that is the method, we can apply for any case.
No, but what is the analysis that you want to do where you are applying the test voltage? Is it to find output impedance?
No, not the output impedance.
Or
to find out the signs. They explained using that technique. It will be generalized technique so that we can apply for any problem.
Okay, so like I could not understand the argument. Can you repeat once again?
They have replaced the op amp.
Okay, they have replaced the op amp with what?
They have put A and B like that only.
Okay.
And they have replaced and they have put a test source which is connected to the gate, which is connected to the this what we call as our gate of this circuit.
It is connected to the gate of the MOSFET.
MOSFET.
Okay. Then
that I don't know. I am not having now the steps what to do, but they have done like that. If that is the method, then it can be applied for any circuit.
I'm not aware of this method, to be honest. I don't know. I have not gone through this method, so I cannot comment.
Okay.
But yeah, because here the moment I saw this current source VG and all, I could relate it to the CS amplifier, and because I have an idea of CS amplifier, that's why I went with this particular approach. So yeah. Right.
They are asking ratio of VDD by VG, madam.
They are asking for the ratio of VDD by VG, right? In the same problem. VDD by VG. Okay, since there is no current flowing, this is VDD. Then here we will have VDD by 2. VDD versus VG, right?
VDD by VG.
VDD by VG, no? Okay. So in this circuit, here you have VDD by 2. That same VDD by 2 will translate to A, considering it a ideal op amp. And the current that is flowing from VDD to ground is GMVG. This is the current that is flowing. So the current that will flow between VDD minus VDD by 2 upon R will also be GM into VG. Correct? So this is VDD by 2R is GMVG. So VDD by VG will be GMR twice. 2 times GM into R. What was the answer?
Yeah, that one only, madam.
This one only, no? Yeah. Because there is no current.
Considering feedback current is 0, no, ma'am?
Yeah, that is always zero. That's what I said. No, there won't be any input current in the op amp. We always say that.
Means in feedback we are going to take only voltage.
Yes. Unless there is some other path where your current can flow. If there is no other path, only you have a path which is connecting the input of your op amp, then there won't be any current flow. It is always the case. Is this clear?
Clear, madam. Is op amp having an output current VG? Sorry, IG.
Yes, output current. Okay, but here since it is uh, connected to gate of
Hmm.
MOSFET, there should not be any output current. But there are definitely output resistance, right? So that output current will flow through that output resistance and go to ground in the op amp itself, in the op amp's internal circuit itself.
In
But
this
op amp,
case, there is no output current for this op amp, ma'am.
there should not be any output current. And also from the circuit, you can see, right? Until VG, let's say you have a current IG. But after that, where is that IG going? It is an open circuit, right? There is no connection to any component or there is no connection to ground, right? After VG. So it is open circuited. In an open circuit case, will you have any current? You can never have a current, right?
No, madam, it is not open circuit. You said it is a small signal model of MOSFET, right?
Yeah, in case of small signal model, how
Then
does
the
it look
output
like?
current is going to gate terminal.
Gate terminal के बाद कहाँ? I'm saying no that gate does not carry any current. In MOSFET, there is no gate current. That is also evident from the small signal model, this small signal model, and from this model as well. Because there is no connection between VG and ground, right? Ground is at S. Here, this is open circuited, right? So, will there any IG be flowing? Is there any connection to ground where your current can flow? No, right? So IG is always zero. So gate current is always zero.
Okay.
And MOSFET.
Then in week 5, first question, madam. Here I am sharing my screen.
Okay. Week 5, first question. Okay, what is the first question? A filter is having almost constant magnitude passband transition with the variation of variation from plus minus 6%, and the magnitude of stop band transition at most 1% of passband transition. Find A max. A filter is having almost constant magnitude passband transition with a variation of plus minus 6%. And the magnitude of stop band is at most 1% of passband transition. Find A max. No, please show me the constant magnitude passband. Is this filter discussed in lectures where they are taking reference from? Because just looking at this question, I
And
feel
they are discussed about Chebyshev filters, and they are not discussed about Butterworth filter. Generalized low pass filter, high pass filter, they discussed.
right.
Regarding this type of questions, they are not discussed, madam.
No, because if I'm reading just the problem, I feel the problem is incomplete. The question seems incomplete. Can you show me the solutions, what they have referred to, and how they are solving? Maybe I can get some idea from there.
These solutions are visible, madam.
Yeah, they are visible. What
And
is
in this
point?
solution, I did not understand why they took 0.94 as the maximum gain. From that, they are taking plus or minus 6% means, which is 0.06. From where they took 0.94.
No, that is my question as well.
No.
Where are they taking it as 0.96? So, do they mean the maximum value of gain that they can attain is 1?
Okay.
That is 0 dB.
Hmm.
Because 0.96 plus 0.06 will give you 1,
Okay.
right?
Hmm.
So, based on that, it is 1. Then, what is 0.88? Where is it coming from?
Means they did 0.94 minus 0.06, then they got 0.88, madam.
But how can it be A max?
No, I don't know. That's why I'm asking.
No, this is something I cannot relate to be very honest.
Similarly, second question also, madam. In this assignment, all questions will be like this only.
Is it a Butterworth filter or a Chebyshev filter?
Yeah, so I'm asking that. So, like, are they referring to some filter which was already discussed in the lectures?
Madam,
Because
here they did not mention whether it is
no,
Butterworth
no,
or
that's
Chebyshev.
what I'm saying. In the question, just
But
by
in
reading the question, I cannot comment on anything because I feel there is some information missing. But
week 6 they mentioned Chebyshev filters, madam.
because here I can feel that because I don't have, there is a lot of information missing.
Hmm.
Right. Because how do I know that my passband gain would be 1 dB, 0 dB or 1 volt by volt? It needs to be mentioned in some way or the other, right? Say it is
Hmm.
some type of filter with a maximum gain of 1. So from there, I can. So just by reading the statement of the problem, I feel it's a little incomplete. There is a lot that I cannot make out from the problem itself.
Suppose this type of questions they will in exam, then how to solve, madam?
No, definitely. See, exam cannot be this open ended, right?
Hmm.
Exams are because it's a national level exam,
But
and
in the analysis,
definitely people will be giving you, and it's not like you are looking at the lectures and from the same lecture you are getting the question. That is not true. It will be a random paper with random questions. One question from say first week, and the next question from say eighth week. Again, it's from second week. So it will be all haphazard. So that's why more clarity is always preferred in an exam, and definitely clarity would be.
if question is related to contents, then we can solve. If they give you the question like this, how to solve?
No, definitely there would be more clarity in exam.
But they are considered this as a in the evaluation, right, madam?
No, but I feel they are referring to some filter which has already been discussed in the lectures because I have not gone through the lectures, so I am not very sure which filter they are referring to. But they must have discussed some filter in lecture or in tutorial, and they are taking it as a base and they have created these problems. That's what my guess is.
So every question will be like this only. See here, madam, what is the order of filter n? Third question they mentioned it is a Butterworth filter.
Huh.
Then how to solve this one, madam? Third one.
Okay, for Butterworth filter, the specifications of Butterworth low pass filter are given as FP, Amax, FS, and Amin. So for Butterworth filters, there is this formula, and based on the formula, you have to fit in your all these. So from FS, FP, Amax, Amin, all from all these values, you will get. Uh, this Butterworth filters transfer function is there, and by place using these values you can find the order there. So it is specifically related to Butterworth has the transfer function already designed, so it always have a fixed transfer function, and you need to use the um coefficients. The Butterworth coefficients are
Uh,
already defined, so
yeah, in
you
this solution, I feel one doubt, madam. I'll share you that. If you
okay.
see this one, madam, they are given the transfer function, whatever you said, correct. So
Yes.
see here, madam. For this A max,
Hmm.
they are taking 10 log. If I'll go to Amin, they took 20 log. I think it is 20 log, right, madam?
No, no, there also it would have been 20 log. It must be root under. So they have divided it by 2. That must be the case.
Not understand, madam.
No, no. So it's like 20 log root under 1 plus epsilon square hone se it would give you the same thing, right?
Will you explain about this transfer function and formulas, madam, once?
Transfer function, I have to take them out from my knowledge
Because
because
I confused with this, madam. For Amin, they took 20 log. For Amax, they took 10.
no, no, there also it should have been 20. It's just wahan pe bhi there would have been a square root like that of that in the this second case, but when you remove the square root, that power of 1 by 2 it will come in this, right? So it is like if I write 20 log root under 1 plus epsilon square, I can convert that is 20 log
How
1
we got
plus
root underscore 1 epsilon square, madam? From where we got that?
this is magnitude, right? So magnitudes are always in square of root under something,
We
right?
required some transfer function, then from that only we can find the
Yes,
magnitude.
yes, yes.
So we don't know first what is the transfer function from, then how can we write it is a 20 log of square root of 1 plus epsilon square?
So you people, so in lectures was Butterworth filter not covered? The transfer function for Butterworth filters?
No, madam. No, madam.
Oh, okay, okay. Actually, I have to bring up my
See,
notes.
I listened all the videos, madam. If you see here, all videos I listened. Even I saw the tutorials,
Hmm.
but I did not find those things.
Butterworth filter was not covered.
Yeah, in week 6 they covered Chebyshev filter.
Okay.
Yeah, here they did not cover Butterworth filter.
Because Butterworth filter, they have a given specific this
In this
transfer
filter,
function.
simply they are discussed about low pass, high pass, and band pass, madam.
No, no, but in
That too
Butterworth
with the help
filter,
of RLC, and they explained about filter transformation, how to convert a low pass filter in or transform into an high pass filter. Those things they are explained.
so for Butterworth filters, they already have transfer functions defined. Like first order Butterworth filter have a certain transfer function. It is simple transfer function, but from second order, you have a certain transfer function defined, and also there are coefficients corresponding to that. So Butterworth filter
Generally, for filter,
have
we'll mention only one cutoff frequency, right, madam? If it is low pass or high pass.
yeah, yeah.
But here they mentioned a pass band frequency as well as stop band frequency. Means it
So
allows starting from 20 kilohertz, or it will allow up to 20 kilohertz. Later from 20K to 30K, it doesn't allow. What it mean, I did not understand actually.
okay, so this is something very specific with Butterworth filters.
Will you explain me, madam?
Yeah. Uh, Actually, I also don't have a very detailed analysis. You can refer to a book, but in basic, if
Madam,
you
in forum I asked about that filter design book, but they did not share till now.
uh, these filters is covered in which book? The analysis. Filters are covered.
All questions are like this only, madam. What is the
Some
order of
signal,
filtering?
some
And
signal processing based books are there, no, where they design filters. Signal processing may they do. So those books maybe you can refer to, because as these, as I'm mentioning, Butterworth filters come with coefficients. So like it will have a given transfer function. That transfer function is fixed for Butterworth filter, and also in the transfer function, the coefficients are also fixed. So since the coefficients are fixed, while designing a Butterworth filter, based on the coefficients, you have to select your R and C values in such a way that Butterworth
that I know, madam, how to solve these questions. That I am asking.
um, so it is you'd need a thorough analysis for Butterworth filters. That is the thing that I can tell, because it is a
Yesterday
different.
also I asked you, and you said that today we'll discuss.
No, Butterworth filter we didn't come, right? When did we say
Madam,
Butterworth? Otherwise,
yesterday I shown you all these things, these questions.
but I
In
don't know
last,
which question is what, right? Which week, which question is what? How would I know?
yes,
I
madam,
don't
yes,
have
madam.
the
In
answer, right?
last tutorial we are discussed only week 3, and you
Yeah.
said we'll discuss in tomorrow.
Yeah, but I didn't know the topics. Otherwise, I would have prepared and come Butterworth
Then
filter.
we'll go to week 6, madam.
Because Butterworth filter is a whole, matlab, it is a, so if I'll tell you, Butterworth filters already have transfer functions for first order, second order, third order, fourth order. Their transfer functions are already fixed. You can refer to some standard signal processing based books where they focus more on filter designing. So there you can find Butterworth filter. Butterworth filter is well known, but it needs a little analysis. So transfer functions are fixed, the coefficients are fixed. So from there, those coefficients and everything, you deduce your cutoff frequencies and everything. So the parameters which are given to you, they will come into picture there. So you can look into it
Ma-
a little.
Madam, if we are able to read the things from the textbook, why we are going to listen these NPTEL courses, or why we are registered these courses?
I cannot answer you that, but I didn't know this. So Butterworth is never discussed in lectures because I have not gone through the lectures, so I have no idea.
Shall I open that video? Then it is clear to you.
Okay, because if it is not discussed, I believe it should not have been given. But since I'm not the designer, so I cannot comment. I'm
Yes,
not.
madam. Then how to solve those questions if they comes in exam? If I
Uh,
ask in forum, they are saying ask in problem solving session.
no, but if Butterworth is not discussed, then you would need to go through in books, most probably. Yeah. Chebyshev, likewise, see, Chebyshev low pass filters are there, no? So Chebyshev low pass filters were already discussed in the course. You are muted. You're muted. Am I audible?
Yeah, yes, madam. For second
Chebyshev,
question, when I saw using their, I got 1, but they are given answer as 3.
okay, so did you go through their solution?
Uh, yes, madam.
Okay, so what are they saying? Okay, so these lectures are little different from the set of lectures that I have. Okay, okay. Because we are given a set of lectures, and following to them we have the problems. So those lectures and problems we are referring to for this problem solving session. But the topics that you people are reading are a little different from what we have. So that's why we didn't have idea about these filters that they
Then
have
we'll ask to
discussed.
whom, madam?
Yeah, these topics are not there in the list of lectures that we have access to.
Okay, I can understand from your end, madam. Then we can whom to ask to rectify my doubts.
But anyways, so in general, see, you have understood Chebyshev filters, right? So by using your understanding, are you able to understand the solutions which are given there?
Yes, madam. But when I simplify, I got 1, but they got it as 3 answer.
So maybe you can cross check your answer once again, and also their calculations once again.
Verified, madam. But by using their formula only I simplified, but I got 1.
Oh, so there might be somebody might be doing a silly mistake. It's basic silly mistake, right? The concept remains same, right? So it might be a silly mistake from your side or from their side, that you people are getting two different answers. Otherwise, using the same formula and same method, you should never get two different answers, correct? There must be some mistake from somebody's end. That is the only possible answer that we can say. Yeah, but any other conceptual doubt that you have other than this? So I didn't know that Butterworth filter was discussed in this detail, because the lectures that you people are accessing to, the set of lectures are a bit different now that I observe. Because the set of lectures that we are referring to prepare your problems and the problems that are
In
already there.
problem solving, you are explained about RC phase shift and Wien bridge.
Yes,
But
yes.
the questions appeared in the assignment are quite opposite. They are nowhere related to your Greenwich or RC phase shift oscillator. Generally, they are given one circuit and they are asked whether they oscillate or not.
And were the lectures in that direction?
No, madam.
Okay.
Earlier, also I discussed with you these things.
Yeah. So that question, so I already clarified in last class, right? You can look through the lectures. So there I could come to the conclusion for what we were discussing. You can go through that notes as well as. Any other doubts? Anything that you're left with? Any conceptual doubt that you feel this concept was not uh, discussed or something? Okay, maybe you can, if you don't have any doubts that can, uh, that are like general doubts, then maybe we can take up somebody else's doubts. And regarding your problems with Butterworth, so I didn't know that Butterworth filters were discussed in such detail. So maybe you can look through some standard book and go through it once. If you don't understand it, then we can discuss once again. So you can share that book. You have my email ID, so you can share your concerns with me once you are going through. So you can share the book that you have referred to. I'll go through it once, and then we can discuss the problems again. Okay.
We don't have book, madam. That's why I'm asking. Otherwise, I
No,
can
no,
read
you
from the
can
textbook.
see, when you search in Google, you can get an ample of good books, right? And if there are, so was there any reference given? Like, were there any reference books given in the course? Basics. And let's circuits for filters. Maybe you can unshare your screen. Yeah. Meanwhile, anyone else has any doubts? The concepts that we have discussed till now. Filters. Anyone has any other doubts? Oh, clamper. Okay. So somebody asked clampers, right? Shweta, clampers, it is actually a lengthier topic. It would take me 10-15 minutes. And next session of the second TA is about to start at 8 p.m. And hopefully he might be discussing the problems on week 8, because I thought of going for doubt solving session. So he must be discussing week 8 problems. So there he would take up the problems on camper. So maybe you can attend his lecture. And if just in case you still have doubt, you want some clarity, then you can write to me. Then I can share with you prepared notes or something. Okay, because if I take up time now, you would miss the second lecture that I don't want. Because in the next lecture that is starting from 8 p.m. by the next second TA, he must be taking up the problems on clampers, right? And he would solve problems based on week 8 most probably. So there you can attend. But still, if you have some doubt, yeah, you can write to me. You have my email ID, right? So my email ID is always there. So you can write to me in case of doubt. Okay? Because I don't want to take up clamper in haste. Clampers is a good topic and it needs better clarity. So that's why, right? So you can ask the TA. He will be taking up most probably clampers. And still, if you have doubt, you can feel free to write to me. Yeah. Okay. Okay. Anybody else? Shweta, any doubts? Shweta?
No, ma'am.
Okay. So if there are no doubts, maybe we can break over here. And that's all for today. Thank you. Hope to meet you people and some other session some other day. That's all. Thank you. All the best for the exams.
Thank you, ma'am.
Okay. Bye, everyone. So I'm Dishada Devi signing off from Analog Circuits course for the live problem solving sessions. Thank you.